Do you ever hold a finger over the mouth of your hose to make the water go farther? Do you ever experience pain in your ears when you jump in the deep end of the pool? Why do these things happen? The answer lies in the theories and equations of fluid mechanics. Fluid mechanics is the branch of physics that studies the properties of fluids in different scenarios, especially how fluids react to forces acting upon them.
Fluids are things that easily deform with external pressure and don't have a fixed shape.
Essentially liquid and gases. Fluid mechanics can be split up into hydrostatics and hydrodynamics. Let's start with the basics of hydrostatics. This is the study of the properties of fluids that aren't flowing. Buoyancy, which is why objects float, is a good place to start. Buoyancy is the upward force exerted by a fluid on an object submerged in the fluid. That buoyant force is equal to the weight of the fluid the object displaces. This is the Archimedes principle. Say you have a ball submerged in water. If the weight of the ball is less than the weight of the water displaced, the buoyant force will be greater than the gravitational force on the ball and cause it to rise. In other words, if the density of the ball is less than the density of the water, then the ball will float. The ball will continue to rise until the weight of the water displaced by the ball is equal to the weight of the ball. Although water's density doesn't change much with depth, its pressure does. This explains why our ears hurt when diving to the bottom of the deep end of the pool. As the depth increases, the water pressure your eardrums experience increases too. Using conservation of energy, Bernoulli showed that as the water's potential energy decreases with depth, its pressure energy increases. To demonstrate that pressure increases with depth, consider a column of water. A deeper puncture would spew water out farther than a shallower puncture. A bend or other shape change in the pipe would not change this relationship. Hydrodynamics is the study of moving fluids. Bernoulli also showed that combinations of potential and pressure energy can be converted into kinetic energy and back. This explains why if we blow between two sheets of paper, they will move towards each other. The faster moving air, which is the fluid, reduces the pressure so that it exerts less force on the paper than the still air on the outsides. The greater forces outside push the papers towards each other. Meanwhile, volume flow rate continuity is another equation useful in hydrodynamics. The equation tells us that as the cross-sectional area decreases, the velocity of the fluid increases and vice versa. It shows us why holding a finger over the mouth of your hose makes the water go farther. When we block off a part of the hose, we are essentially reducing the cross-sectional area of the hose opening, increasing the velocity of the water that comes out. Bernoulli's equation is the most famous equation in fluid mechanics, but it only accounts for non-viscous, steady-flowing ideal fluids. The more general Euler's equation also takes into consideration unsteady and rotational flows. It can tell us about shockwaves and tornadoes. Euler's equation can be derived from the Navier-Stokes equation. It is more powerful because it also applies to viscous fluids and can model swirling, turbulent flows. Computer simulations using these equations can help us determine many things from the aerodynamics of a race car to how blood flows and distributes medicine throughout the body. At the core, all three of these equations, along with the continuity equation, represent conservation of energy and mass for fluids.
So next time you're watering those out-of-reach plants, you know what to think: fluid mechanics and Bernoulli's equation. Thanks for watching.